Welcome back. We are in chapter 16 on temperature and heat, and this is section 16.2, heat capacity and specific heat. When we think about putting heat into an object, its change in temperature is proportional to the heat that we put in. I mentioned in the last section that temperature is a measure of the average kinetic energy of the random motion of particles. So heat, temperature, and energy, they're all related. The idea is we put in heat, which is energy that raises the average kinetic energy, and that manifests itself as a rise in temperature. We have this equation that you see. It says Q. Now we're going to use Q to mean the heat that goes into an object or a substance, equals, and that's a capital C underlined there, heat capacity of the object as measured in joules per Kelvin times the change in temperature. And for change in temperature, we're going to use Kelvin or Celsius degrees. Because a Celsius degree is equivalent to a Kelvin, then that means that if you increase by 1 Celsius degree, you're also increasing by 1 Kelvin. So it could be Kelvin or Celsius degrees. So sometimes in these formulas, such as you see down below, a little glimpse of this, sometimes you'll see Kelvin, sometimes you'll see Celsius degree, and if you're referring to a change in temperature, a Kelvin is a Celsius degree. All right, well, let's continue on down on the next line. So heat equals, now notice this line, this is going to be the line, the equation that's much more useful to us in this class. Instead of saying capital C, the heat capacity of the entire object, let's break down that heat capacity into its mass times the specific heat of the substance. So it's the mass of the object times every substance, whether it's aluminum, copper, steel, water, whatever it is, has its own specific heat. So this equation where my pointer is at, that's the main equation you'll be using for these types of problems. Q equals mc delta T. For specific heat, you can look in the book at table 16.1. It gives the specific heats of about a dozen different substances. So as you're doing the homework, you can refer to that table, but I just mentioned too here aluminum. Its specific heat is 900 joules per kilogram Kelvin. And what we'll see later is what that has to do with is if you put in 900 joules of heat, then it will raise 1 kilogram of aluminum by 1 Kelvin. Now, we could use other units. You could also look at that as calories per gram Celsius degree, and it's 0.215 calories of heat will raise 1 gram of aluminum by 1 Celsius degree. By the way, that's also kilocalories per kilogram Celsius degree. A kilocalorie is when you look on the nutrition labels of foods and it says calories, those are actually kilocalories. You can also see for steel, another example is 502. Now just a comparison between those, aluminum being 900 joules per kilogram Kelvin and steel being 502 joules per kilogram Kelvin. You can think of that 900 that aluminum has as a measure of its resistance to changing temperature. So you think about it this way. If you wanted to if you had 1 kilogram of aluminum and you wanted to raise its temperature by 1 Kelvin, you would have to put in 900 joules of heat. However, if you wanted to do the same thing with a kilogram of steel, you would only have to put in 502 joules of heat. The steel will change temperature more quickly. It doesn't need as much heat to change its temperature. So aluminum having a higher specific heat than steel, you can think of it this way. It has a higher resistance to change in temperature. Now, if we take that equation, you see it on the right, Q equals mc delta T. Sometimes we know the amount of heat that's put in. We want to know what's the temperature going to be. So Q over mc. Now, liquid water has a very high specific heat, And that means it has a very good high resistance to change in temperature. You can put in a lot of heat and it's not going to go up so much. So liquid water, its specific heat is 4184 joules per kilogram Kelvin. And that's a good number to have memorized because we're going to use it so much in this class. By the way, that's equivalent to 1.00 calories per gram Celsius degree. It's not a coincidence that it's exactly 1.00. That actually is the basis of the definition of calorie. So this means that if you want to raise 1 kilogram of water by 1 Kelvin, you need to put in 4184 joules. Or if you want to raise 1 gram by 1 Celsius degree, which by the way is also a Kelvin, you have to put in 1 calorie of heat. So we look at this example, the heat to raise the temperature of 1 kilogram of steel versus aluminum by 20 Celsius degrees. If you're talking about steel, the heat we put in is, we're using the equation Q equals mc delta T. So M, 1 kilogram times C, 502 times 20 Celsius degrees. Notice I put in a plus sign there because it's going up in temperature. So it's going to be a positive 10,040 joules. However, if we want to do the same with aluminum, raising its temperature by 20 degrees, we have to put in more heat because it's more resistant to that heat, 18,000 joules. Now we could also ask, what about the heat to lower the temperature? Let's do this with aluminum. Well, we're still going to use Q equals mc delta T, but notice what delta T is. Remember, delta is always final minus initial. If you're lowering the temperature, final minus initial temperature is going to be negative 20 Celsius degrees. So it's the same 18,000 joules that it takes to raise it, but this comes out as negative. Q equals negative 18,000 joules means we actually have to extract 18,000 joules from that aluminum. Here's some definitions. 1 calorie, notice I write that with a lowercase c. It is by definition the heat to raise 1 gram of water by 1 Celsius degree. And a conversion that'll be useful for you, 1 calorie is 4.184 joules. 1 food calorie, notice I write it with a capital C to distinguish from a normal calorie. This is actually a kilocalorie. But in our society, modern conventions on nutrition labels, we just call them calories. But that's 4,184 joules. By definition, it is being 1,000 calories. It's the heat to raise 1 kilogram of water by 1 Celsius degree. And if it ever comes up, here's a conversion into English units. 1 BTU, which is a British thermal unit, is equal to 1,054 joules. It is by definition the heat needed to raise 1 pound of water by 1 Fahrenheit degree. Let's look at example 16.1 in the book. It says your whole family has showered before you, dropping the temperature in the water heater to 18 degrees Celsius. If the heater holds 150 kilograms of water, how much energy will it take to bring it up to 50 degrees Celsius? If the energy is supplied by a 5 kilowatt electric heating element, how long will that take? All right, so the problem at hand is we need to raise 150 kilograms of water. We're raising it from 18 degrees Celsius to 50 degrees Celsius, and the power is 5 kilowatts. Well, first we want to know how much energy will it take? That's what the question asks. So energy, Q equals mc delta T. So we've got the mass, the specific heat of water. Delta T is 50 minus 18. That's final minus initial temperature. And we get 2.008 times 10 to the 7th joules. That's the amount of energy it's going to require. Now, if we've got a heater that is 5 kilowatts, that's 5,000 watts or 5,000 joules per second. If power is defined as Q over T, then T is Q over P. So we do the heat that we found up in the line above, divide by the 5,000 joules per second, and we get 4,017 seconds, a bit over an hour, 67 minutes. And I want to point out what I've said before, that if we're talking about a rise in temperature, a change in temperature, then a Kelvin is the same as Celsius degree. Now, there's the idea of thermal equilibrium. Let's say we have two objects. And you can look at this picture down below. We could be talking about maybe a very hot object. Imagine a hot lump of metal, and we put it into water. So water is the other object. Then when these two objects are in thermal contact with each other, heat will flow from the higher temperature object to the lower temperature object. All of the heat that is lost by the hot object will be gained into the cooler object. So we can say Q1 plus Q2 equals 0. Now, we have to be careful with our definitions. As I said earlier, Q is defined as the heat that goes into an object. But keep in mind, the hot object is actually going to lose heat, which means its Q is going to be negative. So we've got a negative amount plus a positive amount, and if energy is conserved between the two of them, that should come out to be 0. Practically, realistically speaking, you're probably actually going to get a bit of heat lost into the environment. We can think of the air, the surrounding air, as a third object. But if we use an insulator, something that's well insulated, a double styrofoam cup with a nice lid, we can keep that to a minimum, that loss of energy. And so for purposes of these homework problems, we'll just assume that energy is conserved between the two objects and say that Q1 plus Q2 equals 0. In practical situations, that's not going to be absolutely true. But as we break down those Qs, what that means is for the first object, we'll call it M1C1 delta T1, plus for the second object, M2C2 delta T2 is going to equal 0. Also, I want to iterate that assuming in this equation as I've written it, the hot object is object 1, that entire term is going to be negative. And it'll come out negative because delta T, final minus initial, because it started out hot, it's going to lose temperature, it's going to go down in temperature, so that delta T1 will make it negative. Let me take you through example 16.2 in the book. It says an aluminum frying pan of mass 1.5 kilograms is at 180 degrees Celsius when it's plunged into a sink containing 8 kilograms of water at 20 degrees Celsius. Assuming that none of the water boils and that no heat is lost to the surroundings, find the equilibrium temperature of the water and pan. When you do the homework problems at the end of this chapter, as I'm recording this, I have numbers 35 and 38 assigned, and those are example variations. They are variations of this example right here. So make sure that you understand the example that I'm taking you through now before you attempt those problems. So I've written out the given information. We're dealing with a 1.5 kilogram pan that starts out at 180 degrees Celsius. What I didn't mention is that it's made of aluminum. I didn't write that down. And we're also dealing with 8 kilograms of water at 20 degrees Celsius. And we want to solve for the equilibrium temperature. The hot pan is going to lose heat into the water. It's going to go down in temperature from 180 to 170 to 160. The water is going to creep up in temperature 20, 21, 22, and eventually they're going to meet somewhere in the middle. That's the equilibrium temperature. So I'm going to use the equation Q1 plus Q2 equals 0, or you can think of it as Q pan plus Q water equals 0. And then right away in the green ink, I broke it down. So instead of saying Q pan or Q sub P, I just wrote MP Cp delta Tp. And then for Q water, I just wrote M water C water delta T water. You add them together, they equal 0. We want to solve for T. So at this point, it becomes just algebra, recognizing that delta Tp is T minus Tp, and T without the subscript is that equilibrium temperature we're looking for. And delta T water becomes T minus T water being the initial temperature of the water. Now we go through the algebra. We're going to distribute the MC terms. And you notice in this line where my pointer's at, the first and third term, I've got them underlined, have the equilibrium temperature. I go through the algebra, I skip some steps, but I trust that you can follow along the algebra. And we're going to separate just the t terms to the left and the TP and TW terms to the right. So we're going to add MPCP-TP and MWCW-TW, getting them over to the right. Then we're going to factor out, with the terms that are left on the left, factor out T, and that's going to leave us with MPCP plus MWCW. We're going to divide by that. And in the end, as you go through those 2 or 3 lines of algebra, you should be left with, here's the final temperature. Plug in all those values and you get 26 degrees Celsius. Even though usually when you're plugging in a temperature, not a change in temperature, but an actual temperature, you need to do Kelvin. In this case, you can actually get away with just using Celsius. And it seems a little weird that you can get away with plugging in Celsius equation or Celsius values. But the reason is it came from these differences in temperature. Because the problem dealt with differences in temperature, Celsius is okay to use. And if you don't trust that, you could also convert these temperatures in the beginning to Kelvin, run through this, and you'll see you'll get a Kelvin answer, which is going to be the same as this Celsius answer. But you look at it and you see the final temperature is 26 degrees Celsius. What that means is the water went up by only 6 Celsius degrees. The pan went down by a whopping 154 Celsius degrees. Big difference in change. Well, that has to do with that the water has such a greater, first of all, mass than the pan. The water was 8 kilograms versus a 1.5 kilogram pan. But also the water had more of a specific heat than aluminum. So overall, the water had a greater heat capacity than the pan, so it had greater resistance to that change in temperature. I want to take you through this next example, which has an interesting result. Rather than mixing different substances, I want to mix different masses at different temperatures of the same substance and see what happens. And the reason I'm doing this is on the next page you'll see there's a very interesting result. And in fact, what I'm going to show you is you can do this problem, you can estimate this problem just by drawing a picture, doing no math at all, just by drawing a picture and using a bit of estimation. But I'll get to that picture on the next page. Let's say we're mixing 5 kilograms. This is all water, so 5 kilograms at 10 degrees Celsius. 2 kilograms at 40 degrees Celsius, and 3 kilograms at 80 degrees Celsius. They will all come to an equilibrium temperature. We pour the cold water, the warm water, and the hot water together. What's the final temperature going to be? Well, let's go through the equation. Q1 plus Q2 plus Q3. So we say M1C1 delta T1 plus M2C delta T2, I should have written C2 right there, and plus M3C delta T3. And it occurs to me I didn't need to write C1, C2, and C3. I did write it correctly because it's all the same substance. It's all water, so we can just actually drop that subscript. It is appropriate to have C. The next step I do, in fact, is I just divide out C. Because it's all the same specific heat, we can divide the entire equation by the specific heat, C, and it drops out. Now I'm expanding the delta T1, the delta T2, and the delta T3. So it's M1 T minus T1 plus M2 T minus T2 plus M3 T minus T3 equals 0. Let's now distribute those M's. And what I've done, you can see in very small print, I've underlined all the T's. The final, that equilibrium T, because that is what we want to isolate. That's what we want to solve for. So we have M1T minus M1T1 plus M2T minus M2T2 plus M3T minus M3T3. And I want to isolate all the T terms, keep them on the left. All the others, the T1s, T2s, and T3s, we're going to put them over to the right. As you go through the algebra and you solve for T, you get this equation. Now this equation may look somewhat familiar to you because it looks exactly like a center of mass equation. If you replace those t's with x's, you've got the equation for center of mass. Remember back when we learned center of mass in first semester, it was x equals m1x1 plus m2x2 plus m3x3 divided by the sum of the masses. Well, this is very interesting because what this means is that if we were to take a thermometer, now a thermometer is a linear way of measuring temperature. So if we were to take a thermometer and lay it down on its side, such as you see right there, it measures from 0 to 90. Now this looks just like in first semester, we might lay down a meter stick. Well, this one only goes up to 90 centimeters, but it's linear, so it measures distances. So those are now measurements of degrees. And if we could set on top of this thermometer of negligible mass the different masses, 5 kilograms, 2 kilograms, 3 kilograms, at the different temperatures, and then you imagine if I could put my finger under this at one position, where do I put my finger so as to balance this thing? Maybe somewhere around here-ish. That's where it would balance, maybe somewhere around here. That is how we can estimate what the equilibrium temperature is. It's the same as the center of mass on this configuration. Well, we can actually put the values that I gave on the previous page, and it comes out to be 37 degrees Celsius. If we do a center of mass equation, as we learned it last semester, it's 37 centimeters. So it's the same thing. So it's a neat way to quickly estimate, just by thinking of it as a center of mass balancing problem, what is the equilibrium temperature. This works for different masses, but keep in mind, it only works when you have the same specific heat. So in general, it has to be the same substance. Let's look now at problem number 55 in the back of the chapter. Number 55 says a 1.2 kilogram iron tea kettle sits on a 2 kilowatt stove burner. If it takes 5.4 minutes to bring the kettle and the water in it from 20 degrees Celsius to the boiling point, how much water is in the kettle? So I've written down that the temperature is going from 20 to 100 degrees Celsius. We have the mass of the kettle, M sub K. The power is 2,000 watts. And the time, it says, is 5.4 minutes. We'll convert that to 324 seconds. And we can calculate what is the mass of the water. And we're going to start by saying Q equals MWCW delta T plus MKCK delta T. Now this is not an example of heat going from one substance to the other. In fact, the tea kettle with the water in it they both start at room temperature, 20 degrees, and an external stove is going to provide power. It's going to provide an amount of heat that will bring up their temperatures, both of their temperatures, up to 100 degrees Celsius. So we have that the heat provided is mass of the water, C of the water, delta T, plus mass of the water, C of the kettle, plus delta T. I didn't bother to distinguish delta T of the water and delta T of the kettle. They're the same thing. They're both going from 20 degrees to 100 degrees, so I just call it delta T. Well, I change this up a little and I substitute. We really care about the power, not the heat itself. So Q equals PT. I made that substitution. Also, while I'm at it, I factored out delta T. Probably not a necessary step. In fact, as I'm looking at it, I'm thinking probably the quickest course of action would just be to solve straight for mass of water. I didn't do that, but let's just follow how I did it. If you want to, you can go ahead on your own and solve it by just going through the algebra and solving straight for mass of water. Well, as I have it here, then what I've done from this line is I've divided both sides by delta T and then subtracted MKCK. That leaves me on the right-hand side with just MWCW, as everything else I've put to the left-hand side, and then I divide by CW. So in the end, mass of the water is all this that you see on the screen. PT divided by delta temperature minus MKCK over CW. I plug in the values that I get either from the table of specific heats or given in the problem, and I get that the mass of the water is 1.81 kilograms. I'll just round that for two significant figures to 1.8 kilograms. That is the end of section 16.2. You're now equipped to get started on the homework. Have a great day.